So I'm going to change the topic a little bit, break the sequence slightly, because I think so far, almost 2 weeks, we have been talking about systems and all, and we haven't talked about serious engineering. And I want to talk about a little bit about the serious engineering today. So I mentioned to you last time that I want to summarize all of the structural mechanics knowledge that we will need for this course, and the details will be in different courses that you will have together. But I want to make sure that you understand what you need to bring back to do your project and finish this course. So fundamentals, go back to basics, very, very much basics, and build from there. Okay, so it's kind of a review of the structural mechanics, especially the dynamics. Let's start with history. So you can call him as the first person who started to think about structures as we know. So it was not too long ago, 1600s, not that long. So he's formulated the concept of inertia, that bodies, resist, they don't want to move, before Newton, actually. So he started this whole idea. And so I would say this is the starting of the engineering concepts and dynamics as we know now. And then this guy, Robert Hooke, almost same time, a few years later, he started to think about the proportionality concept, that if you move something, then the displacements and the force, they are somehow proportional. But he never wrote the Hooke's law that we call it Hooke's law. That is a misconception. But he only said that these two are related. And he just said, as the extension, so the force. So in Latin, it was pronounced like that. So he started the concept of linearity, and that guy started the concept of dynamics in a way. So these are the people who started the engineering gradually. And then came Newton. He formed almost similar time, almost same time, different parts of the world. And he formulated the first equation that we all know, correlating his idea and his idea in some way, and say, okay, force is actually an acceleration, the movement are related by this function, that the force and acceleration are related by mass or mass, and they're related like this. So this is, of course, fundamental equation we all know now. So this is the start of the real physics in a way, and also engineering in some way. And then this guy came nearly after 200 years after that, long time in history. Imagine, 200 years. Now it's 5 years. You cannot even, 1 year, you can't even read what's going on. 200 years passed between that idea of, and his putting this equation there, correlating stress and strain, and finding the Young's modulus as a relationship between them, and finally have an equation, and finding that stiffness between that. So he started the same concept, but he looked at the stress and strain in the similar manner and came up with the relationship. So this actually led to the equation of F is equal to KU in a way, because this was similar to this idea and that idea put together, we get the equation and so-called the Hooke's law, or the Hooke's equation, or the stiffness equation, that force and displacement are related by stiffness, and stress and strain are related by also stiffness, called Young's modulus, or E. Okay. And we discussed all these things in the previous class. So this is just a quick historical perspective on how these things developed until 1800s. And that's where things start to move very fast. Let's go back again. Let's look at a body. I'm talking about physics now, 10th grade or 8th grade or whatever. And it's moving as a mass, and it's moving, and if you want to move it from 0 to something, you will need to have some acceleration. And that is given by F is equal to ma. And A is a derivative of displacement. So now they're thinking about acceleration, but engineers are thinking about displacement. So we like to think about acceleration as a displacement derivative, second derivative. And then we also have the displacement of a static system. This is system in motion. It's not in equilibrium. It's moving, so it's not equilibrium. And then we have the equilibrium where it is not moving, but we have the force, and then we also have a force here, we also have a force here. Here, we are restraining it from moving, so a force is generated. And then this is displacement and force are related by the stiffness of the system that is standing. So now you can see here the two are completely opposite. One is moving, a rigid body, and the second one is the body is trying not to move because it's fixed and that something is holding it back. Here, the mass is holding it back as inertia. Here, the stiffness is holding it back because it's connected to ground. So these two systems are the first one. Again, engineer's view and physics view of the motion. But if you combine them together, you get this equation that you get the mass, acceleration plus stiffness, and together. So now we are saying that the body is not really free to move a lot, but it's free to move within that rapidly. So it's not slowly moving, it's rapidly moving, it's accelerating, but it cannot go too far because it's connected to the ground. So now the force has two components, the mass and acceleration component and the stiffness and displacement component. So now we have the total equilibrium, but it's in equilibrium now. It's a dynamic equilibrium. But this is still a stick. K is still a stick. K is just a number. It's not representing a real physical system. It's not a column. It's just a stick with K. It could be anything. It could be a spring. It could be whatever. So it's not, it's a concept. It's not real body yet. So, but if we make that into a real body, like a column, then it is made of some material. So when that column will have stiffness, it will also bend and deform, and its material, its molecules will move. It will internally try to change something, and that will give rise to damping because it's internally doesn't want to change its structure. So the damping comes up. So now you also have damping of the system, damping of the restraining system coming up to hold it down. So it's not just a concept or a stick, but it's actual member made up of material. So we have material damping. Other types of dampings will also come, but the concept of damping starts from here. Okay, so you have damping here. Now we have a fuller equation of the force equilibrium with mass acceleration, velocity damping, and stiffness and displacement. So now we start to build the dynamic equilibrium of a system which has all the basic ingredients of a typical structure. But still, it's lacking one thing. What is that? Something very important is lacking. Okay, if not, let's go on. And then people said, okay, what if the motion was because of the ground acceleration? Who's moving it? So the mass could be moving by 2-3 ways. Somebody is attaching a motor, an actuator, and moving it, or it's on a shake table, or it's on something is moving it, right, rapidly. So that could be, so if it's a ground motion, then this force Ft with varying time is now related to the ground motion, acceleration, plus the mass. So we have force coming from the movement of the ground. So now we have a ground motion equation, equilibrium equation. This is a force equilibrium equation, force vibration. This is coming from the ground acceleration or ground movement. And I'm sure you're all studying this with spending much better than I can teach. But now we come back to this idea. So Hooke's law says that the extension is proportional to force all the time, forever and ever, right? Which is not true, because no structure can move forever and ever. At some point, it has to stop moving or stop deforming. It has to have. So this is the force, linear response. So that is the force, that is the displacement. So you can continue with this line forever, because that's what Hooke was saying, right? But then observations prove that he was not right, because actual response measured by the people when they start to test things was like this, like the class project that you did. When you tested the beam, it did not go that way, it go this way. So that means when people started doing physical tests, they've realized that Robert Hooke's law is actually not valid all the time. It's only valid part of the time. And that's the nonlinearity came in. So the blue response is the real one, and the black response is the assumed one. So then that means we have to go back and adjust our equations for this observation, right? So we took this nonlinearity. So now at any given displacement, please carefully see this one. At a given displacement u, there is a linear force coming from the linear equation, and there's a nonlinear force coming from the nonlinear response. And there's a difference between linear and nonlinear response. And that is a correction that we need to make from linear to go back to the reality, right? To the real response to correct that number. And we are looking for that number now. How much is the correction that we should make? It seems obvious that we can, this is the difference, but the problem is the blue line is not known unless you test it and destroy it. So if blue line is not known, we have to figure out the blue line through iteration, iteratively finding it, searching it for this blue line step by step, looking for it in the darkness, literally, so trying to search where the blue line is, right? So we need to have this correction, delta F, found somehow, gradually during the process. And then we have the force. So now force is equal to Ku plus the correction, plus or minus, depending upon which direction is. That means we have to correct now the force, our equilibrium equation, F, to be corrected from the linear part to be the nonlinear part. So we need to add this correction to our equation. So we go back here and we add this newfound observation that the force is actually like this. And then we go back and then combine it with the dynamic equation. And we say, okay, now Ku plus another correction force has come up. So the total equilibrium now has the components of mass and acceleration, has the component of damping and velocity, has the component of stiffness and linear stiffness and displacement, plus a nonlinear correction factor. Once we do that, then perfect. We now have solved the real structures problem completely because we have considered everything now that can be considered. Nothing is outside of this equation anymore. And then we combine this back to the ground motion. We have the full nonlinear dynamic movement equilibrium equation. So that's the summary of all of the structural mechanics that you need to know, right? So now we have the tools. We have many tools actually here in this sheet, and we can use those tools selectively for doing many things based on what information we have, how much knowledge we have, how much tools we have, how much money people are paying us to do many things. So let's look at this equation a little bit now, because we are going to do the analysis for seismic forces or even for wind, similar way. And then we expand that equation and see what can we get out of this equation, the final big equation. Just like we derived this for the section analysis, this equation is the basis for all analysis. Okay. And this one, out of that, you can now derive so many equations by making simplifications and making assumptions. First assumption is that there is no damping and there is no external force, there is no ground motion, is thus the building standing there by itself. Building or structure standing by itself without forces, without anything, just pure mass and stiffness. If we take that thing out, then we get the modal response or free vibration equation comes out from there. And that will be converted to equivalent static, which I will show you later using response spectrum, or other cases, you can just convert that into an equivalent static force analysis. Then you can also do response spectrum from this one, which we will talk about, and then the pushover analysis and the linear time history analysis, and of course, the nonlinear time history analysis. So every type of analysis that you do for any structure is right there in this slide and in this equation, right? So now all we need to decide is how much data we have, what kind of tools we have, and what do we want to do. In fact, in general, all of them will be needed. For a practical project, you will need to do almost all of them. You will need to do response spectrum analysis. You might need to do pushover analysis. You can also do linear time history, nonlinear time history, equivalent static, definitely modal. So you will need to do all of these analyses to understand the full behavior of the structure and then compare and then fully get full understanding of the structure. So this is the sheet that we can now use as a reference to go forward today, right? And then we will discuss each one of them one by one, just summary, because there's whole subjects behind that. So we have natural response simplified with factors, what the code is using. So the codes use this formula to do the seismic force, equivalent force design. They will give you formulas and factors to calculate this one. And then we ignore nonlinearity, we get that one. We ignore inertia, we get pushover. We get response spectrum by maximizing maximum response. And then the real one is here. So now everything else that we do is an approximation. If you really want to determine the real response or the true response of a structure, we need to do full nonlinear dynamic time history analysis. And everything else is a subset and has some approximation built into that. So that's the foundation of the work that we are talking about. There are other analysis methods, capacity spectrum, incremental dynamic, multi-degrees, so many probabilistic, many other concepts come in, which we will discuss gradually. So just, the picture is not completely complete. There are other things that also are attached to that or related to that. Go back again to understand this basic equation once again, and then see what we can do now step by step. So this is the system, conceptual system. There's a mass, there's a spring, stiffness, there's a damping, there's a force, and then you have this equation that represents the basic dynamic equilibrium. Okay, and that is the image that you must have seen in so many books. External force, mass acceleration, damping velocity, and stiffness displacement, and nonlinearity correction. And nonlinearity itself may be like this one. So nonlinearity may come from stiffness, damping, and even from other sources. Mass is normally not nonlinear, but it can come from changes in damping, changing in stiffness. So both stiffness and damping can change with displacement. So which mean, or velocity or acceleration. So which means that they are also nonlinear. So nonlinearity is contributing from this whole equation being inside. That's the definition of nonlinearity, that the solution is embedded in the solution kind of thing, right? That's why you need iteration to solve this one. So let's get back to dynamic analysis of tall buildings and see some of the things now that we have the fundamentals summarized. So where's the doctor doing here? You're all too young. Probably you don't go to the hospital as mentioned to you as often as sometimes people like myself or older people have to go, annual checkup, which I do every 2 years. But the first thing when you go, they will ask you to sit down over there and let's take your pulse and measure your heart rate and blood pressure before doing anything else. Even if I have to show my teeth, they will like to get my blood pressure and my heart rate, right? Whatever. They will always do this. The first thing from the patient is to do that. Okay. Heart rate, and many of us now wear these devices to measure the heart rate when we're walking, when we're sleeping, when we're doing something. So heart rate is so important that it's an indicator. It's like one basic, simple indicator of everything, right? That if you know the heart rate, there are stories about old doctors in villages, who didn't have anything else. So they will just put their, put their fingers on the pulse. And from that, they could diagnose every illness in the world. True or false, we don't know, but that's what they did. But some had the capability just to measure the heart rate and the variation, and they would know what's wrong. Okay, that's the experts. They just look at one thing without tests, and they know what's going on. And then now we have doctors, they do 30 tests and find nothing because they just, unfortunately not looking for the right thing or too many things. Okay, anyway, moving forward. So the heart rate is an indicator of the body's state and potential for any problems due to other causes. So this is an indicator of things to go wrong, right, in a human body. It's very well known now, right? If that is the case, is there a similar thing for structures? So let's look at the heartbeat of the structure, right, in the same way. And the answer is clear. It's here. The modal response. Because This is pure and simple structure, nothing else. Just the structure by itself, sitting down, not moving on a chair, and just wanting to be measured. And that is the heartbeat, which is the modal response. So you determine that by stiffness and mass and nothing else. And once you do that, everything else can depend on that. So let's get into that, the modal response. So to get the modal response, we delete everything from the equation and we go to the basic equation, and this is then solved. It's by many ways. There are, it's the math and so many you all know, and I don't want to go there. But this is how somehow is solved, and it can result into two things, and then those two things give you tons of information. Actually, I can have 3-4 hours of discussion just on this topic. Of course, we don't have 3 or 4 hours, so I'll just summarize. So natural response or the modal response is the heartbeat of the structure. That's the first thing, as I mentioned to you. Indicates stiffness and mass relationship because it only has those two, stiffness and mass. So it determines the relationship of these two basic intrinsic properties of the structure from which the structure is made of. If it is physical, it must have stiffness and it must have mass, which means that you can determine the relationship between them, relatively stiff or soft or heavy or whatever, from this one. And this is based for damping, resonance, amplification, and all the other effects can be calculated from there. And there are many relationships which are available to get this estimate for tall buildings, from tests, from simple numerical, so people can guess them based on the data collected from millions of thousands of buildings earlier. Okay. So, and then of course we can calculate it. So modal response relies on three things, three output that you can get. Number one, natural period. So natural period is the time it takes for the building or a structure to complete one oscillation, one complete cycle of vibration. From this, go back and come back to the original state. One complete cycle, time taken is in seconds, is natural period. Frequency is number of these oscillations in 1 second, reverse of natural period. So you get the frequency from that frequency. Some people like to use frequency. Mechanical engineers use frequency. We prefer to use natural period. It's more indicative. And then mode shapes, which is the deformation corresponding to the frequency, the natural, because the structure can deform in many ways. For every vibration possibility, there is a associated natural period or frequency. So that shape of deformation, mode shape, is connected to that frequency or connected to that natural period. They come as a set. Okay, so we get this information from modal analysis of that equation, and then the natural period, the periods and mode shapes are inherent properties of structure. So these are properties of the structure, do not depend on loading. Do they remain constant? Does the natural period of a building remain constant? That over a period of time, the damage will change the stiffness, and then it will change the natural, and that's how you measure how much age there is. It's like dating, carbon dating of the fossils is the same thing. Is the dating of the structure can be done by measuring its response. And there are as many modes as degrees of freedom in the system. So there is million degrees of freedom, there are million modes. Okay. Not all modes are important though. So our job as structural engineers is going to be more important. Find the significant important modes, search for them and integrate them. Then local modes will come up. Local modes, we will talk about that, are the modes that shouldn't be there or are not important, but they are giving you false results. Just like the tests that doctors do gets a lot of data that is not important. They're not looking for the right one. So these are the local modes that mess up the data and then disrupt if the people do not understand, they might be sort of led astray by these local modes because they are not one that we're looking for, or sometimes we're looking for local, not global, and I will explain later. Then most important is the last one, higher mode effects are very important for tall buildings, which are not important for other structures. So we will focus on higher mode effects as well. That what is higher mode effect and how do they change the response? So we will discuss many of these things, local modes and higher modes and significant modes. So the first thing is in your project, when you do, which we will start, actually, I want to talk about the project today, and we should start soon. 4 groups, I think we will make and start. So the first thing that you should do is to do a modal analysis of the structure before doing gravity, dead load, live load. Forget about them. They don't matter. The first thing you must do is the modal analysis and to check many things, which we will learn in a way. Then after you do this one, then you can do response spectrum, time history, pushover. Everything will depend on the modal analysis. So that has to be done first and verified and just check everything. The structure is okay. So there are many anecdotes or many stories about modal response and people or engineers either not understanding them or misinterpreting them. For example, if you have a tall building and it has a small antenna on the top, then when you do the model, the model internal frequency analysis, that antenna will start to move first before the building moves. So the first mode will be the antenna mode. And some people may think that to be the building's mode, which is not true. And then whole thing, oh, my first mode is so, totally outside, and they don't understand what happened to the first mode because it's not the mode of the building, but it's a local mode of one part of the building, right? So many times this kind of things disrupt the view. So this is showing you the different modes of a tall building. This is the first mode. This is the second mode. This is the third mode. Now you can see all 3 modes side by side, first, second, and third in different directions, right? And this is the most common response you should get. This weak direction, strong direction, and torsion for a symmetrical building. Second modes now, you can see the form is very different now. And third mode in the weaker direction. So first, second, and third mode, you can see the deformation patterns in each one of them, how the higher modes are now exciting different. Other direction, 3 modes on the stronger direction. It's like dance moves, right? And then the 3 modes in the strong axis. So far 6 modes, and then torsional mode, first one, torsional mode, second one, twisting, 1970s dance twists, and then the third mode. So now you can see all the 3 modes here. So the point is that these modes, as you can see from here, obviously there's fun and all of that stuff, but they capture so much information there. Their order, their magnitude, their shape, their sequence, everything has so much meaning. If you are looking for it, this is where all the information about the structure is. Like I said, the guy who just holds the pulse and can tell everything, this is the one. And if you know how to read the pulse, you are an expert. If you don't know how to read the pulse, you're just looking at them and you say, what is this? It's an animation. You have no meaning to you. It's just simply structure dancing. But if you have understanding, then a lot of information is hidden in this video, right? And you can later come back to explore that. Okay, so they exhibit the strength and weakness of the structure, can be used to check whether they are within reasonable range or not. Natural period, for example, looks okay or not, right? You should have some idea about that. Then you can also see disconnected members. If the building, one of the beam was not connected, that beam will move first before the building. So it will start to to animate separately, or some member which is not connected will have its own local mode activated before the structure. So you can see whether you forgot to connect one beam with the column or the program did not model it correctly. Okay. Then local modes are identified that may need to be suppressed, like I say, the antenna. You may have to set the frequency that please don't include the antenna in my analysis because that's going to disrupt that. Okay. So you look for the right modes from that. The symmetry of the structure can be checked, whether it's a symmetrical, unsymmetrical structure, because I told you symmetrical structure typically have this order: weak mode, strong mode, torsion, weak mode, strong mode, torsion in second, third, fourth, fifth, and so on. In that sequence, if the sequence is broken, that means building is unsymmetrical somewhere, right? And then the first mode is rotational, structure is definitely unsymmetrical. Actually, not true. This is, I should correct myself, which I always do that, say and then correct. For perfectly symmetrical structure, actually it's possible to get torsional mode as the first mode, in which situation that can happen. The rule is that the structure is symmetrical, the first mode should not be torsional. But in a perfectly symmetrical structure, it's possible to get the first mode as torsion. Any idea why? Yes, stiff tube and weaker outside. So if you have a very weak framing outside and very stiff wall in the middle, then the building will start to rotate about the wall because the rotational stiffness is too small compared to the bending, because the bending is prevented. So wall tube doesn't have a large torsional stiffness, should need to come from the outside. So there are situations where the rule also needs to be broken. So as they say, you should know the rules, but also know when to break them. So that's one of the areas where you need to break the rule. Then the resonance, applied loads or excitation can be avoided. This is, I showed you that collapse where the people were jumping, matching with the natural frequency of that stadium last time, and it collapsed or it fell down. So the resonance load frequency versus natural frequency must not match. You know very well. So if you're doing the army or you're into that, which I was, you are supposed to, when you're marching in as a group, when you arrive at the bridge, you must not march in step. You must break the step, because it's possible that your marching frequency will match with the natural frequency of the bridge and you might break it, right? So those kind of things are based on this resonance, again, coming from understanding of the natural frequencies. This is a typical building, where this is a symmetrical building. As I mentioned to you, weak direction, strong direction, torsion. This is unsymmetrical building. The first mode is torsion. So a building will start to twist about so if the stiffness center and the mass center are not at the same location, you will get unsymmetrical response. So the building tends to rotate. The stiffness and mass are the only two things, and they have to be at the same location for building to be symmetrical. If you move the mass out, then there is eccentricity, and then the torsional mode will come in. If you move the stiffness out, same thing. So mass and stiffness, eccentricity must be very small or zero. This is one way to check whether the building is going to respond symmetrically or not, to look at the modes. This is another real building, and you can see here 3 modes: first, second, third. So this is not, this is first mode is a little bit torsional because you can see there the shear walls are at the corner, not at the center. So they are causing the building to twist, right, in the mode 1. And then mode 2 is this way, is more or less correct. Third mode is again torsion. So if the 2 out of first 3 modes are torsion, that also means the building is pretty unsymmetrical. So that's how you quickly check the animations, and you check the thing, and then you should come up with very good information about that. For tall buildings, this table is extremely important. Now, this table is like, if you know how to read this table, this contains a lot of information, huge amount of information. Why? Please now carefully. First, look at the things in the table. Number 1, natural period in seconds. Number 2, the mass participation in that mode, which means how much mass was moving in the building to cause this mode to happen, because not all the mass can move for each mode. If it's a simple building, cantilever, simple building, small structure, first mode will move all of the building. If it's a frame, 100% of the mass will move because it's just a frame building. But if it's a tall building, complex configurations, then some mass is not moving in each mode because modes are now complicated. And the building is very tall and stiff and big. So, which means that in the first mode, in this page, this cell says that the first mode, this is the direction, it is moving in minor direction. So building has minor and major direction. One of the first tasks you will do in your project is to find out the building's primary directions, minor and major, and their angles, right? Symmetry and so on. Okay. So you find out the minor angle, and then you say that you found that the first mode is 5.3 seconds, and it's 60% minor direction, 60% mass is moving. So 5.3 seconds is pretty long for a building to move. So 5 seconds, 1, 2, 3, 4, 5, around that much to complete one cycle. It's pretty slow. So building is moving very, very slowly. So building like this for a ground motion will not respond very quickly because it's just taking its time. So ground motion will not be affecting it so much because the ground is moving very fast, much faster than this period. So excitement to this will be very low. Short building will have very small initial period. They will respond very quickly. So we'll come to that in a minute. But this is important that what is the natural period of the building? So the typical rule is very rough rule. There are many rules. Number of stories divided by 10, 0.1 n. So if the building is 50 story, this natural first mode should be around 5 seconds, and which it is. This building is 55 stories. It's coming out with 5.6. Very good. Good design. Looks good. So you look at that and then you say, oh, that's nice. And it's moving in the minor direction, which is also good. So it's not bad. And that 60% of the mass is moving. For analysis to work or for the building to complete its analysis, you must collect enough modes to move at least 90 or 95% of the mass. So first mode, which means is not enough to do the analysis. It's only 60%. In each direction, you must collect 95 to 100%, 95 above mass participation, so that you capture all of the forces generated by the mass. So which means in this case, first mode is not going to be enough. Now, if I move in this direction, second mode in the minor direction, so this is T1. If I just look at this sequence of the natural period as given by the program, T2 is here. Second mode is just like you saw in the animation, is in the major direction, bigger direction, and the natural period is 4.96 seconds. Now, this number shows what? Because mass of the building is the same, did not change. So why did these numbers change in one direction and the other direction? Come on, people, there are only two variables, mass and stiffness. If the mass did not change, the stiffness must have changed, correct? Which means that the stiffness in two directions is not the same. This is very important observation. And this can tell you how much difference is in the stiffness of the building in two directions, right? So which means that the building is weaker in one direction and stronger in the other direction because the natural period is decreasing, which means mass is constant, which means the stiffness must be increasing. The first direction, minor, and second direction is major, and this direction stiffness is more, and I'm getting about 66% of the mass participating in that direction. So in that direction also, first mode is not enough for me because I need 95%. And then it is twisting on the third mode, period of 4.1 seconds. That means torsion is pretty stiff compared to minor and major. First torsional mode is more stiffer than both of the translational mode. 0% mass is participating. That is the idea of torsion. Building is just rotating. No mass is moving. It's just rotating. So no mass is participating from torsion. So you can already see that there are 6, 7, 8 things you can determine from this. I've just got started, right? So we just look at the numbers and these three, and we found so many things that we can understand about the building. Okay, let's go this way now. This is the second mode in the minor direction, which is now T number 6. If it went in sequence, if the building was perfectly symmetrical as it was in our other case that you saw the animation, this should have been T4 because sequence should follow 1, 2, 3, 4, 5, 6, 7, 8, 9. But no, the sequence is broken. The second mode in the minor direction is actually the sixth mode in the order. What happened here now? No direction is already this one. It's now the mode number. The second bending. That's why I showed you that animation. You were not watching. At that time you were just, enjoying yourself. No, the second bending, which has a double curvature, which means that this building has a stiffness distribution not uniform. In the second bending, the stiffness distribution along the height of the minor and the major are not the same. So the minor direction, maybe some shear wall, some column, something is uneven, which attracted the stiffness or moved the stiffness, right? So instead of 4, it became 6, and the 4 went to this one, right? And this 5 went to this one. It should have been 1, 2, 3, 4, 5, 6. So the stiffness distribution now in both direction is not uniform. It started like that, but for the higher mode bending, some stiffnesses are unevenly distributed, which means this building has vertical irregularity, so to speak. It is not uniformly regular in the vertical direction. So this gives us, it was symmetrical in the plan, in the first mode, but not symmetrical in the vertical direction. So you can determine these things also by looking at the order in which they are given. Now, now 18% mass is participating here. So 60 plus 18 is 78. We still didn't reach 95 that we want. That means the building first few modes will not be sufficient for me to calculate the response, right? So in binary direction, I'm still short of the mass participating. Another thing is that look at the initial period, 5.32 to 1.28, a big jump. Unlike here, the jump was small, 5, 4, 4, 5, 1. Order changed. That means the higher modes are much stiffer than lower modes. That's another observation not that we make, because the stiffness is much 5 times larger, 4 times larger for higher mode than the lower mode. Lower modes means 1, 2, 3. Higher modes means higher in the order. Here, 4.96 to 1.56, and then 15%. And here, 1.3 for 4.2. So all modes are significantly more stiffer. That means they require more stiffness to move, right? So now we have this. Then this one, so this should be 1, 2, 3, 4, 5, 6. This is now mode number 9, should have been 7. Once again, same problem. That means minor direction, stiffness distribution is not as we expected or as we should get from a very symmetrical building. Okay. And then 7 here and 8 here, and then they are reversed again. So now this is the mode, double curvature, triple curvature here, and here the mass participation is 6.5%. So 78 plus 6.5 something, 80 something did not reach 90 yet. That means we will have to go further to investigate this building into mode number 12, 13, 14, and so on, until we get to enough modes that we get 95% modal participation in each direction. So sometimes we have to go up to 36 modes, sometimes higher. You keep going until you collect enough mass moving so that the seismic total force can be added up together. But I will show you why that is important. But right now, I just want you to focus on this diagram and see how much information you have here. It's a lot more here. I'm going to stop now for now, because we can come back to that when you, but please do not forget to make this diagram by yourself and analyze it to understand what's happening. Linear response to ground motion. Okay, we have got this one. This is the response of the building which was moving by itself. Nobody was asking you it to move. Natural response. Every building is moving all the time. It is called natural. So no building is standing still. It's just that we don't measure them. But every structure is moving. And they're moving in most of these modes already. They are in motion. And we can always detect, we can always measure it. That's the job. But what happens if we move the building, not because of the natural, we now move it by shaking the ground and we just get the linear response. Now the building will already has its own modes of moving. When you move it externally, it will only move in the modes that it knows, in the order of the stiffness that it knows. So you cannot make it move in any other way than its own modes. So the natural modes now will respond to the ground motion and start moving in their own way. So structure will decide what I'm going to do with this ground motion. So if you put three different structures side by side, you have seen the shake table computations, they will all move differently. Same ground motion, same everything, each structure will respond according to their own modal properties. So but before we go there, this is taken from Professor Murthy's book, very nicely done. First, we should understand, how does earthquake motion reach the building? So it's like he has given this light bulb analogy, which is very nice. And he says that earthquake is like a light in a bulb, and the farther you are, you get less light. So that's simple, and it's very simplistic. But on the way, we have it happens here, so we place of interest. And what happens in between is, actually, I extended this analogy, and I'm saying that, okay, suppose you are an illumination engineer, and I ask you to design the lighting for this room, because when we go to classroom, we say, oh, the lighting is not enough. Some people say, no, it seems enough, right? So let's say, this is very interesting because it'll come back to structures. Let's say I ask the engineer, please design the lighting so that I can read clearly, right? Seems very simple request, but look at the variables involved. First of all, where are you sitting? How far are you from the light? What is the color of your book that you're reading, white or black? How good is your eyesight, right? How are you holding the book? Towards the light or away from the light? Is there any shadow on the book? The questions are so many to be answered before you can calculate the lighting in the room to be designed. And earthquake design is exactly the same. If you want to design the building for earthquake, you have to see where your building is, what is the form of your building, what is in between, what kind of soil is there, what kind of rock is there, what is the direction of your building, what is the natural periods, and so on and so forth. There are so many things that will affect the response, even though the light source is the same. So everybody's getting different light if I put a light here, right? Different capabilities. Somebody will read, for me, now I can read, but before I used to need many glasses all the time, 3-4 glasses I carry. Yeah, that's another thing. When you grow old, actually, it goes the other way. No, that's not true. You need to get something fixed. So the thing is that when your eyesight goes weaker over age, then your ability, same as the structure. As the structure age, the response also becomes less effective. So this is one way, and this is measured on scale. Earthquake is measured in many scales, right? Scale is how people feel the earthquakes, very subjective. How did they read the book, right? Were they frightened? Did they feel it? Were the coffee shaken? But real scale is here for us. It is meaningless. We don't care about that. We want to find out the energy released during the earthquake. We want to find out the ground acceleration that will reach us. We want to find out so many things before we can decide how to respond. Okay, so this is just, and then when the earthquake is transmitted, like I mentioned. On the way, what kind of waves will be generated? What is on the surface? What is the body waves? Where is the rock? Where is the soil? How is the building? What is the structure? All of this will impact your structure's response. So unless you account for all these things, you cannot predict the response to earthquake accurately. And the whole challenge is trying to find that out. Now, going back in history, 77, 70 something, the codes first start to think about trying to design the structure for earthquake. And that's the time that they come up with these factors that will account for all these things, the K factor, the C factor, the I factor, the V factor. There were 6, 7 factors that try to account for everything in this diagram to try to calculate what will be the force generated by the earthquake. Gradually, they become more complicated. Then we say, okay, fine, no, too many. Why don't we just go to the real analysis, which I showed you earlier, this one. So seismic analysis methods, we have all these methods now, right? Depending upon how much information you can get. If you want to do this one, you need to get the ground acceleration. Where do you get that? To do the analysis, you need to have the ground acceleration. So there is a whole field dedicated to calculating or estimating or approximating or predicting the ground acceleration on your building based on so much analysis. Okay. Then nonlinearity, all the nonlinearity needs to be included. Damping, so many types of damping, material damping, modal damping, relay damping, that damping, all have to be included. Mass is easier, not so easy. Mass is also, what mass should I include? Should I include the people or not? Should I include the furniture or not? Should I include the water in the storage tanks or not? Things like that. Even mass is not so easy to decide what should be included because building sometimes is full, sometimes is empty, right? So you have, so many questions come into play when you try to use this one. That's why the building codes just say factor. When I was doing analysis design in my starting age, when my starting time, 1982, 80, our life was very easy. When I joined the company and I asked my seniors, I want to design this, there was a hospital, remember, and I want to design the structure for that, and how should I account for earthquake? And this is in high earthquake seismic zone, not normal in mountain areas. Very important hospital also. And he said, oh, divide this weight of the building by 5. Done. Total force on the building, horizontal force to be calculated. All I had to do was calculate the weight of the building, divide it by 5 and apply that force. That was the famous rule. W by 10 or W by 5. If this is not a seismic zone, W by 10. If it's a seismic zone, W by 5. That was only one factor, W by 1 factor. So, of course, that's all we knew, but that was, since then, things have become really, really complicated in this area. Okay, so that was then, and now then we get all this, then we got response spectrum, then we got pushover, then we got linear time history, and now we have nonlinear time history. So let's talk about linear time history a little bit. So linear time history, coming back to this equation, how to solve this equation now? Because we need to find the displacements from this equation to be able to, because once we know the displacement, we can go back and do the forces. So from this one, remember that the stiffness in this equation, stiffness is very important. Stiffness, if you remember from our previous discussion, stiffness comes from materials, section, member, and structure. So stiffness is everywhere. So when you talk about stiffness, it's just not one number. Stiffness depends on the material, depends on the section size, depends on how many sections, how many members are there, and how the structural form is. Everything, and soil and foundation, and everything comes into stiffness. So stiffness is not, don't underestimate stiffness. It's very, very complicated to assemble and determine. And this is just linear. This is a single degree of freedom system with the mass and stiffness and damping. And this is the equation that I showed you. And you can calculate from there. You can solve it for the displacement by many methods. I have no intention of doing the math. Okay. But just to show that, okay, this can be solved in this way for a single degree of freedom. And from there, using matrices, we expand it to multi-degree of freedom. And for a given ground acceleration, UGT, the deformation response can be determined in using two things, the natural period and the damping, two factors. Basically, those are the ultimate factors that come here. And then so this is the frequency or the natural period, and that's the damping portion. So you can simplify it in that way. So that means now we end up with damping and natural period only to determine because mass on mass is cancelled. Both side equation have mass. So if you solve it properly, you end up with only these two things. So if that is the case, then I can assume a certain damping, and then for different variations of natural period, I should be able to get the results easily from this equation. So that's what makes each building respond differently to the ground motion, because each building's stiffness and natural period are different, right? So just because natural period is different, the ground response to ground motion, even for a single degree of freedom, is different. For multiple degree of freedom, much different. So this is a response for a 3 to 5 story building, 10 to story building, the way they deform, the way they move, again, from Professor Murthy's book, very nice book. And then you can see that. So it's quite clear that each building will respond uniquely to the same ground motion and generate forces and displacements which are unique to that building. Same city, every building will be different or nearly different. So this is the one on the left-hand side is the building moving due to the ground motion, actual movement of the building for a ground motion. And then these are the modes, individual modes. So this final deformation of the building to a ground motion is simply a summation of all of the modes with different scaling factors that are being added at each time. So which means that the total response, because of what I showed you earlier, for a displacement for a ground motion is for a natural period. And because building has different natural periods, for each mode will be added together in different scaling factors. So please watch this one. This is the real displacement for a ground motion, abrupt, random, and this is the individual modal displacements. They're all added together, and you get the summation. And that's how the Newton linear response of the structure to ground motion can be determined, primarily by doing this kind of a ground motion solution for that. And then coming back to this again, so that means now if you have those modes, then the total response of this building to ground motion will be summation of all these complicated modes all the way up to mode 30 to 40, right? So you can see how complex the response will be. Sometimes it's twisting, sometimes it's moving this way, sometimes it's moving that way, sometimes it's confused, it's not moving at all, and so on. So this will be how each building will be so unique, because even if the first mode of any building is the same, second, third, fourth mode will not. It's like a signature. It's like your biometric. So natural response of a building is a biometric. You can compare it to that. It's like a DNA, because it's so unique. No two buildings, no matter how identically they are designed and constructed, physically in the end will have exactly the same natural response for all the modes. Okay? Even small variations will change them at some point or the other. There's a famous case in Pakistan, 2005 earthquake. So in the city, in Islamabad, there is a block of buildings, 12-story high buildings, and exactly the same contractor, same design. Earthquake struck, one building completely collapsed, other states stood still, because the angle buildings were not. So one of the building was slightly made, site is like this. So buildings are like this, four towers. One of the buildings is at a different angle than the 3 towers. this building collapsed because the direction of the movement from the epicenter and the direction and the orientation of the building completely altered the response of that building to Earth so differently that it actually fully collapsed, not just damaged, it collapsed. And other buildings, nothing happened. That much can be the difference in response to the ground motion. Same building, same earthquake. Okay, next we come to response spectrum method. I'm sure you will study all these things, but I'm just giving you a summary of what you will study or what we will use, not actually what we will study. So response spectrum, once again, coming back to this set, is here. We're looking at the maximum response and a spectrum of a collection of maximum response from a ground motions or sets of ground motions. So when you have a ground motion, actually we designed the building for a response spectrum representing something like this. And notice here, there are 3 response spectrums here, which you will study when we will also study. One is called SLE, service level earthquake. That means earthquakes that will come regularly, so to speak. And then DBE, design basis earthquake, for which the code has given you the mapping or the numbers. And then the MCE, the maximum possible earthquake at that site due to the tectonics and everything, right? And so you have 3 response spectrum coming from this response spectrum. Normally has a spectral acceleration on this side. This is a factor of the ground acceleration, and then the natural period on this side. So natural period on this scale and spectral acceleration on that side. And this is the basis for the seismic initial design. First improvement over the equivalent static W/5 factor. So again, coming from the same equation, you solve that, and this displacement now you can solve for different natural periods. You can assume that building has different single degree of freedom building, has different natural period, length is different, mass is different, and then you get response for the same earthquake. This is the ground motion. Using the linear equation, you get the displacement at the top of the single degree of freedom. This is the top displacement. And then you pick the maximum 2.7 inch from here. From the second one, you put 5.9 and this one 7.4. Okay. You pick these different maximum displacements from each plot of the response from the, remember, ground, and this is very important. Some people miss this one. The ground is shaking at a certain acceleration. If the building is rigid, like Newton's building, the building will move at the same acceleration as the ground. But Newton building is not Newton. Building is hour, which means that stiffness and damping, so building is here. So when this one responds, this will respond in its own way, in its own sweet time. And this acceleration is the one that will cause the force, not the ground acceleration. So the spectral acceleration or the acceleration of the structure is the one that will create the force, not the ground acceleration. And a lot of people think that the force generated in structure is ground acceleration multiplied by the mass. That's not true. It's the acceleration of the building or the structure or the mass at a particular location with the corresponding acceleration. So that's the key. So you do that, and then you can plot these maximum displacements against the natural period that you use in that equation. You get this curve. This is called response spectrum. That means it's a spectrum of the maximum displacement for a particular ground motion with different natural periods, right? And we use this as our basis because now we have converted and we did not care that whether they occur simultaneously or not. Actually, they didn't occur at the same time, right? But we still use them. So this is the simplification from the dynamics to equivalent dynamics, you can say, because we remove the time. We just pick the maximum through the entire time history. We pick that and we draw this one. And then this one spectrum, you can read about that, the peak value. So you get this one, and then you can calculate back the forces. So you can convert that into a force because displacement is known. From displacement, you can go back and calculate forces. And then from that, you get the building response, right? So that's the way it will be solved. And then response spectrum. So you can, from this one, you convert it into a force and you solve it. But this force is now coming from the more accurate estimation rather than my estimation of W by 5 or W by 10. Now this is unique, coming from the modal analysis and response spectrum, initial period, and everything is embedded into this one. And multiple modes can be done now. So you can have this one. So once you have that, you can plot an acceleration, velocity, and displacement. And then from that, you can get all these things. And they're all based on spectral, pseudo-spectral acceleration or pseudo-spectral, not the true acceleration. And then you can plot them all in a single graph with different 3 axes. And typically, this is how the codes will show you. So if you go to building code, every building code in the world has a figure something like this, showing you the response spectrum for buildings with different natural periods and the expected acceleration multiplied by the ground acceleration for different soil types and so on, because now soil types comes into play and many things. So this, it becomes the basis for estimating the forces on the structure using linear time history converted to response spectrum, converted to force back. That's the whole idea, that you can just give the natural period and go back and get the response without doing the time history, because you already generated it. Yeah. But that is based on a single degree of freedom system, and then it is extended in that way. Okay. So now this is an interesting, last 2 slides, then we end on this subject. This is an interesting interplay of the response spectrum with the natural period of the same building and different modes. Okay. So please watch this carefully. 2 response spectrum are shown here together. This is Bangkok, yellow line, blue line is Philippines. So it can show you how much stronger the seismic demand in Philippines is compared to Bangkok. That's the first thing that you can notice. Bangkok is very low, Philippines is very high, right? But look at this one. For buildings which are close to 0, that means in Philippines, if the building is 1 story, which the natural period is close to 0, the response will be very high, about 1 G, as much as the full ground acceleration. I'm trying to interpret the blue line first. But if you go together about here, which is about 10-story building, 10-story building, the response will be 0.7 G. So now the force generated in a 10-story building will be about 70% of the force, mass force generated for a 1-story building. Of course, mass is different, but I'm talking about the proportional, right? And when you go to a very tall building, 60-story building, it is only 0.2. So which means for a tall building, very tall building, very small fraction of the mass of the building actually produces the lateral load or the horizontal force. For a small building, low-rise building, 1-story building, it's almost equal to the ground, the G, right? Which is a good thing and not a good thing. If for a tall building, if all of the mass was created to force, it will be impossible to design that building. It just won't work. That is just way too much force, right? You can't. Lucky for us, or whichever way, it drops down, because I was mentioned to you, because of the natural period, not many modes participate. First modes do not participate so much because, so now, but now for the Thailand, Bangkok, the response spectrum is like this. So for a low-rise building, actually it starts with low and it rises up to about 20-story building and then drops again. This is a very unique response spectrum, only found in Mexico and here and a couple of other places because of the soil characteristics, the basin. Because in here there's a basin which is very soft and the rock is very low. So because of that, the ground acceleration coming here is already diluted in some way, because the natural here rock is moving here, the soil building is here. By the time it reaches here, it needs time. So 20-story buildings appear to be most susceptible in Bangkok comparatively then low, below, and above. And this has been proven in many recent events. And then it goes there. But the thing is, for the very tall building, the difference is much lower than low-rise buildings, right? So here, it still has, comparatively large forces compared to the difference here. Here, the difference between this is very large, 8 times, 4 times. Here, maybe 2 times, right? So which means even if a zone doesn't have strong earthquake, in general, tall buildings will get a similar level of forces. This is something that also people do not immediately recognize. Not similar, but not significantly different, right? You can see here, this is 0.1 and this is 1, 10 times. So one-story house in Manila will get 10 times more force for an earthquake than in Bangkok. But a tall building, 60-story, this one will get 0.2, this one will get 0.15 or 1 or something. So only marginally less. So it's not just the seismic demand, but also the building natural period that will govern what will happen. Okay. So this is this is last, no, not last. Another important thing. This is mode number 1, 50-story building, 5.5, and it is contributing 50% of the mass. Because 50%, this is the first mode of the building, and 50% mass is participating in this mode. That means 50% of the mass of the building will be multiplied by approximately 0.18 fraction of the ground acceleration to generate the force, roughly. Okay. So you get the force from the mass from the first mode to be this blue line multiplied here with the 50% of the mass. Second mode is 30%. 30% will be multiplied by a larger ordinate of the response spectrum. So it actually, even though it is 30%, is less than 50%, but the contribution in the force may be higher because now we are on the higher side of the response spectrum curve, because more percentage, and then 10% third mode, but we are now very high. So now we are getting more mass. So this factor multiplied by 10% of the building mass, that's how things are added. So that's what I was trying to tell you, that the higher modes may contribute more to the lateral force generated on the building than the lower modes, because response spectrum over there is very low, right? Now let's go to another case. This is another building which is only 25-story high. So the first mode is already here, taking 80% of the mass, already at a higher altitude. And then 15% is very high, 4% is almost at the top. So 4% of the mass multiplied by that, 15%. But look at the building in Thailand, same building in Thailand, 80% with the maximum ordinate. So obviously this building will get, and then higher modes, less effect because they are now on a declining part of the response spectrum. So the statement that the higher modes contribute more also is related to response spectrum shape. It's mostly true, but not always true. So you have to look at the interaction between natural period, response spectrum, mass participation, everything together.